we want to come up with an electron configuration. So first and foremost, what is the point of an electron configuration? What are we trying to do? Say that again?
Locate.
Locate what?
The element.
We aren't locating an element with an electron configuration. What are we doing? We're locating the electrons. Okay? So we want to be able to identify the electrons. This is notes for me with that big black line. Okay? So our electron configuration explains electron homes. Okay? It's where every single electron goes. Okay? And there's a variety of different ways that we can go through and kind of represent these things. Okay? Officially, the electron configuration isn't just the electron homes. It is the home for every single electron on an individual element. So you're supposed to specify all of them. Okay? So a full-blown electron configuration should look pretty long, depending on where you are on the periodic table. So if we looked at, say, hydrogen, I need to figure out, hey, whoa, look at that. Sort of. If we looked at hydrogen, how many electrons does hydrogen have? It's only one electron, so I only have to explain the location of one electron. Yeah? Okay. So where is that one electron? Okay. It is in the one, where's my pen? Pen. Okay, there's some weird lag going on. That's not too good. Now I'm writing H. It is in the 1s orbital. Fudge. A little better. 1s orbital, right? That one electron. Okay, we want to have some way to code that information so that we don't have to memorize that electron configuration stitch chart or all of those lines that I drew, right? With all the colors and the rainbows and the line, you like all that? That stuff is neat and that's cool, but we probably don't want to have to think through all that, right? Okay? So in that process, what we're trying to do is say, well, how did the periodic table code that information? Okay? Well, we've got that 1 in front, and then we have the S afterwards. Okay? The 1 corresponds to the energy level. That energy level, let's see if I can pull this off. Yeah, that's not 2. It's 2. There's our 3, right? 4. Those are our energy levels, those numbers at the side of the periodic table. Some periodic tables list those, some don't. Okay? For instance, the one I think in your exam doesn't list them. So what could you do right away? You could write those down. Okay? That's the energy level. That's the number that goes in front. Okay? Then we get, let's see, is that going to be clear? I think that might be clear. Then we get the letter that comes afterwards. What does that letter represent? Okay? We could call it the sub-level. That's getting too fancy. Not that I'm about to pick less fancy words. Not even orientation. It's less specific than the orientation. It's our orbital type, which, yes, is a sub-level. Okay? So it's the type of orbital. Well, where is that encoded in the periodic table? Right? Because there's a bunch of different types, right? What were our orbital types? S, P, D, F, G, and H, which we don't have to worry about because we haven't gotten there yet. Okay? We haven't found elements stable enough to get out to that level. So really all we have to worry about S, P, D, and F, okay, as chemists. Okay? As fundamental chemists, we really only need to worry about S and P. Okay? We'll dip our toes into D at kind of an advanced level. We're not going to touch F. Okay? Where is that information encoded in our periodic table?
Isn't S the first 2 columns?
Okay. That information,
except for helium. Helium is the
is encoded, let's see, can I pull this off? We're going to attempt to pull this off. So S we'll call blue, P we'll call red, D we'll call green. Kind of get it so far? There's code in that? Okay, let's see. Those first two columns are classified as the S block. So when I find an element in that block, its outermost electron is going to be in an S-type orbital. Right? We looked at hydrogens. What was hydrogens? 1s. Is it in that S block? Yeah, S. Okay. We said P was red. Wow, that was pretty spot on. It's a little bit wider than I thought. Sorry. Try and fill that in. This is our P block. So when I go through to identify the electron configuration for any element in that block, its outermost electron is going to be found in a p-type orbital. Okay? If I go through to do the D, where's my screen? Oh, wrong thing. That one's really long. Screw that. This is my D block. Oh, got a little carried away. Okay. This is the D block. Okay. So if I find an element that's in that section, I know its outermost electron is going to go into a D-type orbital. So far, so good? Okay. So what we are attempting to do, and of course I didn't color the red down far enough. Right? What we are attempting to do is recognize those patterns and use that to help us determine our electron configurations. Okay, so we looked at hydrogen. It's 1s. Okay? Hydrogen was found. See if we can color code that again. Hydrogen 1s. Hydrogen is right there. Is in the first energy level. Close enough for that circle. Okay? And in that S block. Those of you saying, I didn't really color it in that, well, you're right. Hydrogen and helium can sometimes float off the table. They become a little bit difficult to qualify. But hydrogen and helium are technically part of the S block. So if you notice, I'm shading in an area where there isn't an element. Helium can be placed there. Okay? So we could call it 1s. What if we did helium? Well, where's its outermost electron? It's in the S block, so we'll call it S. Which row is helium in? 1. So its outermost electron would be in the 1s. That explains one of helium's electrons. But helium has 2. Okay? It has one more than hydrogen. So what can I do? Copy the work of hydrogen. So helium's configuration would be 1s, 1s. Blue for the first electron, black for the second electron, yeah? Redundant, right? How do we simplify? We can write that as now 1s2. Yeah? We've added actually an extra number there. That 2 is now a new piece. That 2 technically isn't an extra number. In the other cases, it was also written in there. A number was written in there. What number was written there? A 1. Okay. What does that number correspond to? Okay. It's the number of electrons. Okay. When we condense it, that number of electrons can actually mean something else for us, but only when condensed. Okay, because in that condensed format for helium, it's 1s2. What can that 2 mean for us in this condensed format? Yes, it means there's 2 electrons there, but it also has another piece of information. Remember, where's helium supposed to be placed up on the periodic table? Supposed to be placed. Air quotes. Next to hydrogen. Which column of the S block is the helium in? 2. What's the number? 2. Which column, if we go back to hydrogen, which column of the S block was the hydrogen found in? What's the number? 1. That number can represent the column in the block. So the periodic table has this stuff encoded in it that we can now pull that information out and get to our electron configurations relatively quickly. Are hydrogen and helium too simple? Yeah, okay, so let's make it more difficult. I think I heard someone say aluminum. Cool, I'm fine with that. Aluminum. Okay, you should be able to nail down quick information first. I'm not saying the entire electron configuration. That actually takes time. But you should be able to tell me relatively quickly for aluminum what information. What do you think? The outer block is P. Fantastic. And? There's 3. I'm confused by that. There's 3 electrons in aluminum's P block? So if you're telling me 3 electrons, this is where I'm writing a number. Because that's what that means. That's the number of electrons. Third energy level, okay. That 3 makes sense. It's in the 3rd row. Aluminum, 3rd row, 3. That first number is our energy level. That tells us the row. P, it's in the P block. Which column of the P block is it in? 3p1. Okay. On a multiple choice test, you're going to be given a bunch of electron configurations and be asked, what does this correspond to? So if you've looked at the practice exam, you should see 2 ways to do this. What's the electron configuration for aluminum? And which of these is the electron configuration for aluminum? 2 different answers, right? No, that was the same question. Let's try that again. What is the electron configuration for aluminum? And which element has this electron configuration? Sorry. Right. When looking at, say, the second question, which element has this electron configuration? What do you think we're going to give you? A correct electron configuration or a false one? Correct. It's got to be correct because that's how you answer the question. Okay? Which means in that configuration, everything listed first needs to be correct. Where's the thing that's going to allow me to differentiate which element I've got? That very last thing. So when given the question, which element corresponds to this configuration, you can selectively delete all of those first characters and just look at the last thing and be like, it says P, P block. It says 4, so 4P. It says 4P5, 5th column. You now know the element. The rest of the information was completely obsolete. You didn't need to look at it. Kind of make sense? So that's nice. What if it was the other way around? What is the electron configuration for aluminum? Okay, so that means 5 answers of all this 1s, 2s, 3, 4 s's and p's and d's and all that fun stuff, right? That could be easy to get confused in. Where should your focus start? The end, where you know it's differentiated. So look at your multiple choice answers. Does it say 3p1? Yeah? Cool, that's a possible answer. Does it not say 3p1? What does that mean? That's a wrong answer. Okay? And in talking through tests, what I've found is students will go through and go, okay, that means it's one of these. One of the big things that you should be doing is not your answer is one of these, but your answer is not that, not that, not that. The negative is an exceptionally useful and powerful tool. Failure we can learn from, we can grow with. So if you know what answer it is not, cross that answer out violently. Not so violently you delete the question on the other side of the page. Okay? But get rid of it from your view. Because now you don't have those numbers that you know to be wrong screwing with your brain. Yeah? So now we could go through and look at the rest. Right? So I could start to look backwards at the rest of these numbers. So far, are you with me? Right? Yes?
So when you did earlier, you were saying that you electrons, but then like everything else has a lot, but then they only put like 3p1 when it has like 13.
So every orbital holds only 2 electrons. Okay, so I think I heard some of your question and maybe I didn't. All of it. So let's try. Every orbital holds 2 electrons. Okay. When we look at our notation, though, we can see different numbers other than 2 appear. Okay, sometimes we'll see 1. Why do we see 1 in the case of aluminum? 3p1. Why is it 1?
First column.
It's first column. It's location. So that's awesome. We can use the logistics of where it is in the periodic table to identify it. That's useful. What's the chemistry side of that? There's only 1 electron there. Okay, so it's telling me I only have 1 electron there. There are 13 electrons, right, for aluminum. Right now we've only specified 1. Where are all the other ones? That's the rest of that black stuff. Okay, that black box that we haven't specified in there. What should we expect when we're going to start backfilling that information? What should we expect to happen to the number? Okay. We're here to stay the same. We're here to decrease. You know what I didn't hear? An increase. Why should it not increase? 3 was the highest. Okay. Deciding on whether it stays the same or decreases depends where we're at in that row. If we're starting in the 3p and we backtrack 1, what do we hit? We hit magnesium, which is located where? In the S block. Which row? Try that again.
Oh, row 3.
Row 3. Okay. It is very easy to delete the hydrogen from the table, so it is actually nice that we've got the numbers written there, because that helps. Right? So we know we have a 3s. How many electrons go into that? Right? We should know that the S-type orbital has how many orientations? Orientation. 1 orientation. The orientation has to do with its shape. If it's a sphere and we rotate it, you can't tell it was rotated. There's 1 orientation. There's 1 possible. Each orbital holds 2. Because I am now backfilling, I know how many electrons have to go into that. 2. I have to fill it. So when we talked about what number should appear, we said decrease or stay the same. It didn't decrease, it stayed the same. Why? It depended where we were at on the periodic table. The next thing we could do is we could stepwise slowly through sodium. We've already addressed sodium by saying there were 2 electrons there. So we're going to move to the next level. What's the next level? 2. Intentionally vague. The next level going backwards in our system because we're trying to fill everything out. Okay, the next level's got to be 2. Okay, what should it be? P or S? For the person that shouted, don't say it again. What should it be? It should be the P. How do I know it goes to the P? What comes before 11 from sodium? Okay. 10 from our neon. Where's the neon located? It's in the second row in the P block. So 2P. Which column of the P block? 6th. Okay, to Rion's question. The number changed again. That doesn't say 2. Why does that say 6? Because it can hold 6 electrons. What's holding 6 electrons? 3 different orbitals. The different is a little bit weird. Are they 3 different orbitals? 3 different orbital orientations. You mean the p orbital has different orientations. What does the p orbital look like? It's that dumbbell shape. That dumbbell shape can align along the y-axis. Think of a hammer curl. Okay, if you've gone to the gym. If you haven't, sorry. Okay, or just a normal. What's the other one? Like there's the hammer curl. I know that. The other, just a curl. A normal curl would be on the x-axis. Okay. Where do we get the z on the dumbbell? You grabbed it by the head and you just did that, right? And you just lifted it straight up away from you. Nobody does that. Okay? It's hard to visualize. 3 dimensions. It sucks. Okay, but that's what's happening. Your orbitals are aligning along different axes. Green. There's our p orbital on its x-axis. Blue, ignore the red, okay, is along the y-axis. Those are your p orbitals. And the red aligning along the z-axis. I don't know if you can see it, but my hand is shaking like crazy. Right? Those are the 3 p orbitals, all aligning out on those axes. Okay? That's what we're talking about. Each of those could hold 2 electrons. Okay? So when we're labeling this out, we wanted to condense that. So 2p, instead of saying 2p, 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 I could say 2p2, 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 right? Accounting for the electrons in each orbital. That's still redundant, so I can condense that even further and say 2p6. That 6 corresponds to 2 things. Number, which column were we referencing? At that 2p6, we were referencing neon. Okay. It's also referencing the number of electrons that went in to get us to that point. Does that kind of get you your question? And you got a follow-up on that? Can I finish the configuration first? Yeah? Okay. After we fill out 2p, we've covered all of those. What do we move back to? We'd move to still the second energy level, but now we're in the S block. How many electrons? 2. Now what do we move to? The 1s, and how many? 2. Okay, last second chance, or whatever, words. 2 plus 2 plus 6 plus 2 plus 1. 13. How many electrons went into aluminum? 13. And in particular, how many electrons went into a neutral aluminum is 13. Okay, so everything checks out, we're good. We could now go through and look at the answer. Which ones had 3p? Cool. Cross out the ones that didn't have 3p1. And now go back through and check which ones matched that sequencing. Yeah? So if we were looking at our multiple choice, the first step was which had 3p1. That was the easiest thing. The outermost electron, let's nail that down first. Look at your multiple choice answers. Which one has 3p1? Once you've eliminated all the other answers, you don't have to look at them. Now you just look at the ones that had 3p1 and you backtrack the rest of those configuration that we just addressed in the black box at the bottom. Is that repeated enough for you? Okay. Rian, question.
How do you know when you're working it backwards? How do you know, like, not to go from like magnesium just to sodium? Like, how do you know which one?
So in sequencing through, a lot of this has to do with how full that row is. Right now, from aluminum, we're working backwards. Everything before it must be full. Okay? So that means when I go, where were we? To the 3s2, I went to magnesium. I've now filled it. I don't care about sodium because all sodium is going to be is 3s1. 3s1 and a 3s2 doesn't make sense, because then it would be 3s3. I would put 3 electrons into the s orbital. I'm not allowed to do that. So by looking at magnesium, I've already addressed sodium, because sodium's in the same block, same row.
Okay. So you pretty much go by like the orbit.
Yep, you can go by the orbit type that we've colored in here. Because remember, the orbit type isn't explicitly addressed on the periodic table. Okay? How are we feeling about electron configurations now?
Just wondering, like for like uranium, going back and filling all that.
Go to sleep. Go to sleep. Yeah, if we gave you uranium, have fun. If you have to take 151, they might give you uranium. And yes, would you have to backtrack through? Yes. Okay? That is where having those patterns memorized becomes more useful to answer an explicit question. By an, I mean singular, which means from my point of view, F it, I'm getting it wrong. Okay? Because the utility of that just isn't there for me. Okay? Deciding where that utility line is for you as an individual becomes challenging. Okay? I will fully admit, electron configurations, you're not going to see again. The utility the rest of the semester is minimal at best. What you need to know are the valence electrons. Okay? And that's important. Okay. Shh. You can't take it back. Are we good with electron configurations? Feeling a little better? Okay. There was a reference to valence electrons, because valence electrons are critically important. Okay? Those will show up again in the Lewis structure video, which in theory you've watched. Okay? The valence electrons do come from an electron configuration. The valence electrons are our highest energy electrons. Highest energy level electrons. So here's our electron configuration for aluminum. I know it's a bit sloppy. Are we okay looking at it? Okay. Where's our highest energy level? 3p is not a highest energy level. 3p is a highest energy level and orbital type. I didn't ask for orbital type. I asked for highest energy level. 3. Where's the energy level specified? It's that number out front. There's a 3. There's a 3. How many electrons went into the orbitals that I've boxed? 3. What's the valence count for aluminum? 3. Okay? So we can pull that from our electron configurations, which is neat. Okay? Is there another place that you can pull that from?
Yes.
Yes. Where's that place?
The second letter of the 13. Doesn't that work for all of them?
H?
No, only the 3 of 13 on the top of that.
Like group.
There we go. The valence electrons can also be pulled by looking at the name for each of those columns. Those names, yeah, we could look alkali, earth, all that fun. You don't have to worry about that. Literally the number written at the top. There's a bunch of stuff up there. Can I just like kill it all?
Yeah.
1 yes, good enough. If we go through and take a look, again, there's our aluminum. What we're talking about is that. That 13 is a name. Okay, we could call that the 13th column. That 13 also has useful information in it. What happens when you subtract 10 from 13? You get 3. How many valence electrons did aluminum have? 3. Random blind luck, right? There's no way that would ever make sense. Take a look at oxygen. Subtract 10 from 16. 6. Guess how many valence electrons oxygen has? 6. It's not blind luck, it's true. Your valence electrons are written across the top of the periodic table for our S block and our P block. Don't do the D block. Weird stuff happens there. It's like your brain. Avoid it. Okay? Conveniently, we don't ask about valence for the other ones, so it's okay. Okay? So all you got to do is subtract 10 from it. Or you could look at Roman numerals. The periodic table up on the wall here doesn't have Roman numerals. The one on your exam, I believe, does have Roman numerals. The Roman numerals code across. And, yes?
So does helium have 2 valence electrons?
Helium has 2 valence electrons. Yep. Helium's a little bit weird, because wouldn't you say at minus 10, wouldn't that be 8 valence?
Can't be.
Right? It can't possibly have 8 valence because it only has 2 electrons. Remember, hydrogen and helium float off of the periodic table because they don't follow the patterns quite as cleanly. Okay, that first energy level just has 1 orbital type. Every energy level after that has multiple orbital types, and that's what explains the patterns that we see. Okay? Yes?
What about the elements like before it gets to 10? Like would they have
Before it gets to 10.
like just the amount that it has?
So elements that before it gets to 10 would be 1 and 2. 3, 4, 5, 6, 7, 8, 9, 10, 12. Our transition elements, don't worry about them. All we care about is 1 and 2. How many valence electrons does the hydrogen family have? 1. How many electrons? Valence electrons does the beryllium family have? 2. So the number matches still. Other questions? Some people are giving me gross faces. I'm kind of excited. This looks good to me. Yes? You would subtract by 10 if you're using, I forget which nation, country, state, thing established the 10 names. Because, yeah, there's Roman numerals with letters, and then there's the numbers. And yeah, I don't know who put it up there, but your periodic table does tell you. So you can subtract by 10 from the big numbers. If it's Roman numerals, it's the value of the Roman numeral. So for instance, for oxygen, which we got in green, you'll see that is VI. What is VI? 6. So it's the interpretation of the Roman numeral. Gets you your valence electrons. Okay. Also comes from your electron configuration. Do you believe me? I just heard people talking, so I'm not sure if that was an actual no or yes. So let's take a look at it. Oxygen. Electron configuration. Outermost. P. I saw someone mouth a 4. I accept that. I would have preferred you gave me the number in front first, but okay. P4. 2. It's in the second row. P block, 4th column in the P block. Second row, P block, 4th column of P block. Backfill. What comes before our 2P? Our 2S. That's a horrible 2. Not the greatest S either, but 2S has to be full. Followed by 1S has to be full. What's our highest energy level? How many electrons are found in our highest energy level? 6. Ta-da! See? You don't have to believe me. It's still right. Okay? 6 valence. Okay. We're going to push a little bit. Okay? So there's that coloring that I just did, but much prettier. Okay? Here's... look at the other screen while we deal with this one. Here's our radius thing again. Can we better explain those trends? Yes. Yes, we can. What are those trends? Okay, for those of you trying to be like, I'm not sure I can remember it, that's okay. The pictures give it away. What are your trends? The atomic radius. Larger. So we could write, does that work? Yeah, that doesn't actually, well, if it makes sense to you, it works. I have problems drawing arrows. I derive it, actually, and we'll look at the derivation here in a second. Okay. Down a column makes a lot of sense, right? When we're talking about radius, what's happening? Why is it getting larger? What's getting further from the nucleus? Electrons. Okay? Why would it necessarily be getting larger as we move down?
Because you're adding more.
You're adding more electrons, which is forcing those other electrons out, right? So when we go down a column, it should get bigger. That makes a lot of sense. When we go left to right, what are we doing with the electrons? We're also adding electrons. So clearly, it should get small. Why did it get smaller? Okay. So we hear this theory, well, it's the nucleus. The nucleus is causing it. When we go left to right, the nucleus is stronger because there's more protons, yeah? Because it is stronger, what does it do to those electrons? It pulls them in. So left to right, because the nucleus is stronger, it gets smaller. Yeah? Do you like that argument? For those people being like, is a good answer. What happens if you go down a column to the nucleus? It also gets bigger, and yet what happens to your radius? It gets bigger. So your explanation only covers half the principle. Okay? When we're looking at atomic radius, it's not just the number of electrons. It's not just the number of protons. It's about where those electrons are getting placed with respect to our changing nucleus. What happens as we go down a column? Where's the last electron placed? Lithium, where's the last electron? As a hint, it's S. Give you another hint, it's 2s. Where's the last electron for sodium? 3s. Where's the last electron for potassium? 4s. What's happening to the last electron? It's getting placed where? At a different energy level. That energy level is our radius. It's getting bigger because our last electron is literally getting placed further from the nucleus. Okay? What happens when we go left to right? Where's our last electron for lithium? 2s. Where's the last electron for beryllium? 2s2. The 2 is the number of electrons. I just asked about the last electron. The last electron is getting placed into what orbital? The 2s. Did I change the energy level? No, which means the last electron is going where as far as distance? The exact same place. What should happen to the radius? It should stay the same. Okay? Because the electron's not going anywhere different. It stays the same. What else changes? The number of protons in the nucleus. The nucleus for beryllium is stronger. So while our electron's going in the exact same distance, I now have a stronger nucleus, which means, and it shrinks it a little bit. Okay? So it's not just that our electrons or our nuclei are changing, it's where the electron is located. If our electron's located in a higher energy level, the energy level is going to trump the nucleus change. If the electron's going in at the same energy level, the nucleus now has an effect on the size. Two pieces of information contribute to that story. Make sense? That is a tricky concept. But that's what's going on with it. What happens when we move to boron? Where's that last electron go? 2p. What energy level is that? It's the same energy level, which means same distance, except what else changes? Boron's a stronger nucleus, which means sucks the electrons in just a little bit, so the radius gets smaller. So when we're transitioning with our trends here, the explanation behind them has to do with where the electrons exist. That's why the atomic trends of atomic radius we could not explain earlier on, because we didn't know where electrons existed. Now that we do, we can explain that. Is that a difficult concept for you to deal with? Okay. So I got 3 people saying, nope, that was straightforward and easy. which then I guess means everybody is willing to accept that they should fully be able to explain that on a test. Silence is a bit challenging, but okay. It sounds like you guys are good to go. Okay. For those of you who aren't, you should probably spend some time with me to address that. When it comes to the test and explanation, what do you think? Short answer or multiple choice? Short answer. Trends would be multiple choice. Which of the following atoms is largest? That's straight multiple choice. Why is one atom larger than another? I'm not putting that in a multiple choice because it'll be a dead giveaway is the right answer. Okay? That's where you would have to explain it. Okay? So, switched up the slideshow a little bit, pulled some slides forward. Ionization energy, because this is looking more at electrons. Ionization energy is the amount of energy required to remove an electron. Okay? I don't care if you know the number, it's irrelevant. Okay? What I do care about is that you understand something about the trends. Okay? Largely because I like this conversation. Okay? The next thing that I want you to understand about ionization energy is if I remove an electron from the atom, what happens to it? The atom is now positively charged. So if I'm talking about ionization energy, the end result is that my atom becomes positive. Awesome. You've now understood or shown that you understand what it means to be an electron versus a proton. Fantastic. That's the application stuff of what each of those things meant. Fantastic. Good. Okay, what are our trends? Okay. In general, okay, and I'm going to erase these explanations because these explanations are crap. In general, the ionization energy increases as you go from the bottom to the top. So if I start at the bottom of the periodic table and move to the top one has a large ionization energy. The bottom has a low one. Why would that make sense? What's that?
It gains more electrons as you go down, so if we do it reverse, it loses them.
Not quite. Think about where those electrons were placed. Okay. We're going to be referencing the outermost electron to be removed. If I look at rubidium, I'm removing an electron from what energy level? What energy level? Yes, it would be the valence. Which energy level is the valence for rubidium? 4. I forget it's a periodic table, dang it. Thought it. Oh, it's not francium. I think it's 6. Someone say 5 and get it right. Yeah, you were right. Fine. 5th energy level. If I remove an electron from hydrogen, what energy level am I removing it from? The 1st. Remember that diagram where we drew all those lines? You're like, those are ugly with going upwards and upwards and upwards? The bottom was our 1st energy level. The top was the 7th. To remove an electron, I'm removing it to where? The vacuum. The 7th energy is right next to the vacuum. The 1st is really far away. So to move it all the way out there requires more energy. Look at just those distances. What happens as we move left to right? Right? It increases as we go left to right. Right? That should sound kind of familiar. What happened to our radius as we went left to right? It got smaller, which means the electrons were closer to the nucleus, which means they were lower in energy, which means to remove them, it's going to take even more energy. There we go. That's where the trends are coming from. They're effectively the reverse application of our atomic radii. When you look at those trends, is there anything that stands out at you of like, I don't like that word? Okay. As someone studying and trying to figure out and nail things down so it's perfectly correct, right? Do you really like the phrase, in general? What does in general mean? 4 stars. Not always. Okay? Meaning some of the times this is true, some of the times it's not. Okay? Where I would expect you to be is the in general, the times it's true. Right? Do you really want to show that you understand chemistry? Some of you are like, no, I don't care. Do you want an A? Yes, you do care. You should explain to me why it's in general. Okay, so it might help if we looked at a picture. It totally explains it, doesn't it? Okay, so let's help. We're saying atomic number. So this first dot to the far left that I'm now colored red is what? Rhymes with the gin. Hydrogen, good job. Atomic number increases by 1 and it becomes helium. Atomic number increases and it becomes lithium, followed by beryllium, followed by boron, followed by You got, yeah, that would be correct, carbon. The periodic table is literally, it's not on my screen, for the record, I'm zoomed in. Followed by nitrogen, followed by oxygen, fluorine, okay, neon, right? Okay. So when we talked about the trends, we said across a row, what happens? It gains. Why? What happened to the radius? It got smaller. So look, hydrogen to helium, what happened to the ionization energy? It went up. Lithium to neon, what happened to it? It went up. Cool. Okay. How about hydrogen to lithium? Now we're going down a column. What happened? It went down because lithium is larger. It's closer, right? There. So that matches, right? Perfect. We don't see any weird like zigzags at all in this. Or a zigzag there, right? Lots of zigzags. Anybody notice that those zigzags kind of seem to show up in roughly the same place? It's kind of interesting. It's a hard thing to nail down. You'll notice all sorts of crap happens in here. What's going on there? Transition elements, so ignore those. Okay. Let's take a look at some exceptions. Which ones do you want to look at? As a hint, okay, fine. Never mind. Okay, you want to look at aluminum. Did we address aluminum yet? No, where's aluminum? Sodium, then we get magnesium, then we get aluminum. So we want to address what's going on with our ionizations. Where? Do I care about aluminum to... I should know this better. What's the next one? Silicon. Do I care to look at the trend between aluminum to silicon?
Makes sense.
That one makes sense. That doesn't go against the trend. Which one am I talking about? Magnesium to aluminum. That's trending downwards. That doesn't make any sense. Why would it do that? Okay. Why would it do that? Have you all seen Disney, right? Yeah. It's Disney's fault. It's actually true. Let's take a look at magnesium. Got a hint there. There's not a hint there. I thought there was. It said electron configurations. Explain this. What is the electron configuration for magnesium? Everybody agree? Cool. What is the electron configuration for magnesium after I have ionized it? What does it mean to ionize? Not adding a charge. I removed an electron. By removing an electron, a charge has appeared. Okay, different meaning. So it becomes 1s2, 2s2, 2p6, 3s1. Everybody see that? That changed. Okay. What happened to aluminum? Same deal. What's its electron configuration? Fill it fast. People are shouting out the answer at me. What happens when it becomes aluminum plus 1? we take a look? There. Ta-da! Is it obvious now? Yes. What's obvious? Changed orbital types. Orbital types change all the time. That doesn't always pop up as an exception.
What about sulfur? Because sulfur did the same thing for this.
And sulfur didn't have an orbital change. So the explanation that there's an orbital change type doesn't work. Because sulfur, you're right, is another one that has this exception that isn't doing an orbital change. Same with oxygen, yes. It does have something to do with them being in the same column. What does it mean when they're in the same column? Same family. And if we're in the same family, we act the same. What's causing the chemical reaction? Not ionization energy. The electrons. The electrons are causing the same reaction to happen. In the same family, they have the same rough electron configuration, just larger. That's why we're seeing that parallel. Okay? So again, I would ask, what about those allows us to see this? And this is challenging to understand. Okay? So we're going to simplify this a little bit. When we move to sulfur, it's a little bit more advanced. Okay? But we can do it with this one. So magnesium started as a 3s orbital. So there it is, a 3s orbital. Yeah? How many electrons were in that 3s orbital? 2. So up, down. Yeah? When I ionize it, what happens? Just have one. One up or one down. Doesn't matter. What happens with our aluminum? Okay. I had the 3s orbital, which I'm going to ignore for the moment. No, I'll write it, 3s. And I've got that 3p1, so I could just write the p1 and just say that. Except how many orbitals, p-type orbitals, are there? Is there just one? How many p-type orbitals are there? There are 3, because there's orientations, right? 1, 2, 3. That electron went into which of those orbitals? Any one of them. They're all the same. What happens when I ionize? I remove it. And I would end with just the 3s, right? And that would be fully empty. This is where things become a bit weird and challenging to process. Okay? And to this end, I'm going to stand at the back of the classroom so you can't look at me. Okay? If we think about the human mind, okay, and what it considers beautiful. So if you were to envision the most attractive person you are aware of, this is why you're supposed to look the other way. It's a little embarrassing when you're staring at me. Okay? You may have seen the little internet meme things where they're like, look at so-and-so's face when it's been reflected across. We took the half of their face and then reflected that mirror across. Okay? When they look weird, it's because whoever did it either did it to a not beautiful person or they did a bad picture for that alignment. Classically attractive people have symmetric faces. Okay? Tons of studies have proven this. Same thing happens in chemistry. Okay? So let's take a look at this. Magnesium. What do you think? Does that look symmetric? Fully filled. Nice and beautiful. So this would be a beauty. Let's take a look at aluminum. What happened with aluminum? Is that symmetrical? No. Okay, that's not symmetrical. There was that little wisecrack, right, I made about Disney? Okay. That's a beast. Let's envision that you are now, not saying you aren't, beautiful. You are magnesium. Ionization, I have to put energy in. Okay, so you start beautiful. And I come up to you and say, I've got this bat. when I hit you with this bat, you're going to look, I'm going to get rid of an electron. Okay? Well, what do you think? Does that look very symmetric? No. So what is that one now? That's a beast. I hit you with this bat, and you're going to become a beast. What's your response? No. Yeah, go ahead. Swing away. No, you're going to fight back. Okay? Ionization energy, I'm not asking. I'm saying, I've got this bat. I'm hitting you with it. You're going to fight back. That means how much energy do I have to put in? I have to put in a lot of energy. So what happens to magnesium's ionization energy? It spikes. Because it does not want to become a beast. What happened to aluminum? It became beautiful. And for those of you who are like, I still don't want to get hit with a baseball bat, plastic surgery. Lots of people want to get hit with a baseball bat. Okay? It still takes energy because it's not a pleasant experience. Okay? But if you go through it, you end as a beauty. What is aluminum going to say? Okay, let's go through and do that. Okay? Which means its ionization energy drops. Okay? The combination of magnesium's going up and aluminum's dropping is what breaks the trend. All of the ionization energies are doing something similar back to our electron configurations. Every single one of them. Okay? There are certain cases where you're balancing out the orbitals, which is causing the quote-unquote exceptions. They aren't exceptions. Okay? They're the rule. The trend is the exception. Okay? Electron configurations can do a lot, particularly when you add a little bit of Disney. Kind of, sort of? That, I think, is cool. Yes?
What about the next drop?
The next drop. If we move to, what is it? For this one, it's phosphorus and sulfur. You're not looking at changing between S and P. What you're looking at is a half-filled orbital, p orbital system, versus one that has 2 electrons in one and the other's half-filled. They're both starting out okay looking. One's looking as a beast. If I remove that one, it now looks okay. Okay? So we're looking at half-filled versus fully filled. A half-filled orbital is symmetric as long as all at that energy level are half-filled. Okay? I would recommend drawing out your orbitals with the lines to represent that, because the electron configurations in and of themselves don't show it as clearly. That's one question, so we're moving on. See, there it is. Electron affinity. Not in the textbook, it's only in the slides, but we're going to keep it really short and sweet. Electron affinity is the energy released when an electron is grabbed from the vacuum. So if I'm an atom and I take an electron from the vacuum, it's going to release energy because the vacuum is higher in energy than any of my orbitals. Yeah? Hi. What would my charge become? Negative. I gained an electron. That's what I want you to know. Ta-da! There's trends too. Don't worry about them. If we combine ionization energy and electron affinity together, and some esoteric mathematical system, which probably isn't all that esoteric, but we don't need to worry about it, we end up with the concept of electronegativity. Electronegativity is a way to quantify for elements that make bonds. So you'll notice the entire bottom row and the bottom 2 rows of our normal periodic table don't show up because they typically don't make bonds, at least not stable bonds, so we haven't studied their electronegativities. Okay? So for the majority of the elements that we've studied and looked at, we can identify electronegativities. Electronegativity is the ability for one atom to take electrons, and in particular, bonding electrons from another atom. Probably the single most important concept in all of chemistry. Okay? Understanding that electronegativity trend is massively important. The trend Fluorine's the most, cesium's the least. You're going on that diagonal. Okay? The noble gases, since they don't form compounds, should have what electronegativity? 0. They don't form, we can't study their electronegativities if they don't make compounds. The whole point is looking at bonding electrons. Okay, so that's why the noble gases aren't on there. So if I take a fluorine and I put it near a carbon and they make a bond, fluorine's going to try and steal the electrons from the carbon. If fluorine steals those electrons, what happens to its charge? Becomes negative. What happens to the carbon? Becomes positive. You've all seen the compound sodium chloride, right? Salt. And it is typically represented as what? Na plus and Cl minus. Have you seen that? Why is it plus and minus? The chlorine is taking the electrons from the sodium. Why? Chlorine is more electronegative than the sodium. Electronegativity allows us to predict the ions that come from this. That's pretty cool. Okay? Ionic charges. Electronegativity, ionization, all that comes into play with ionic charges. Okay? With ionic charges, we get this word called isoelectronic. Iso means same. Electronic is just referencing electrons. The electron configuration, it's almost like an ick. You just missed the I, right? Okay. Equal electrons. So we've got all of these charges written up here, because this is copied from the textbook. And you should probably delete some of these because they're stupid to memorize. Okay? Like the tin and the lead shouldn't memorize. Okay? And I'm only aware of one periodic table, which is why I'm walking all the way back here. Okay? You should also memorize zinc, cadmium, and silver. Zinc and cadmium are +2, silver is a +1. Okay? You should have all of those charges memorized. My argument, you only have to memorize those 4. How come you don't have to memorize the rest? Isoelectronic. Desire to have the same electrons. Is there any element on there, say, that we've named as a group, you might be like, yeah, it'd be cool to be part of that group. The noble gases. Wouldn't it be cool to be part of the nobility if I just came along and said, here's, have $1 billion, all the influence you want? No thanks. Right? You'd probably accept that. Elements are doing the same thing. They want to look like the noble gases. Most of human society and nature is based off of trying to look like the nobility. Right? When we build houses, we put windows into it. Why? Because windows were expensive. You put more windows in your house, you're more wealthy. Right? It's showing off that characteristic. Purple. Purple's the color of nobility. Why? Because purple was a crappy, expensive color back when they were making clothes at that level, which meant only the nobility could afford it. So any purple you could make, you would show off because that made it look like you were wealthy. Okay? Sorry to call people out for this, but it's calling me out equally. Apple products aren't exactly cheap. They ain't that much better. You are buying nobility by having that Apple product. Okay? And they've done a phenomenal job marketing that. Okay? But that's where most of our society comes from. Why do you want a fast car? Because it looks cool. Right? What's the point of the car? It's to get you from one point to another. It doesn't matter how it looks. Okay? So there's a lot of this nobility aspect behind our daily lives. Electrons or atoms are much the same. How many electrons does fluorine have? I know it's not on this periodic table, but you can tell me because you guys are awesome and have memorized it. It was 9. How many electrons does helium have? 2. What does fluorine need to do to look like helium? I heard gain. Gain what? Gain protons. Would it still be fluorine? No. Okay? And also it would have to lose protons, not gain them, right? Okay? So we can't change the protons because then it's no longer the element. What can we change? The same electrons. I can change the electrons. To look like helium, what would it need to do? It would have to lose 7 electrons. That's a lot. How many electrons does neon have? What does it have to do to look like neon? Gain 1 electron. By gaining 1 electron, what would its charge become? -1. If you know human nature, you know the common charges. Right? What happens with nitrogen? How many electrons does nitrogen have? 7. To look like helium, what would it have to do? Lose 5. To look like neon, what does it need to do? Gain 3. Which is easier? Gaining 3. So by gaining 3 electrons, it would become noble and a charge of -3. You notice carbon's not on this list. Why are you told to not memorize carbon?
Yeah, there's a little bit could lean towards the.
Carbon has how many electrons? 6. To look like neon, what does it need to do? Gain 4. To look like helium, what does it need to do? Lose 4. Which is easier? They're the same. Guess for the charge for carbon, it can be +4, +3, +2, +1, 0, -1, -2, -3, -4. It can be all of them. Depending at where you're at on the periodic table and how you transition to a noble gas predicts that charge. There are some that are very tricky. That would be pretty much all of the transition metals, which is why you're not required to memorize them. Because they're tricky and they have multiple charges. You know which 3 don't have multiple charges? Zinc, cadmium, and silver. That's why you memorize them. Okay? It's all about trying to look like the noble gases. Last cheat, because you're like, man, I don't want to have to think about that too. You get the periodic table, and what do? +1, +2, -3, -2, -1. You have to write the +3, +2, +2, +1. How long did that take? 10 seconds? You now have all of your common charges identified for the test. How important is it to know those ionic charges? For the first test, not a big deal. For the second test, where you're required to name compounds and identify their charges where necessary, critical. Start memorizing them. Okay? You guys done yet? No? Okay. Chapter 4. I've gotten a lot of questions about study guides. This is as study guide as you're going to get for Chapter 4. Okay? It's in the slides. This is all the cool scientists, what subatomic particles there are, wave nature of light. These are all the topics that we talked about in Chapter 4. You need to understand those topics to be able to answer questions on them. Okay? I've only done it for Chapter 4 and 5. Sorry. Before you get too excited about, oh, this is cool. Yeah, I haven't done it beyond that. Chapter 5, Mendeleev and the periodic table. He's got predictions. How did he come up with those predictions? What are those predictions? Can you predict? The trends in electron orbitals, chemical and physical properties, radius, ionization energy, charges, all that fun stuff we talked about. And that would be cool. That would mean we have an entire day on Tuesday where we can just review, except we're also going to talk about Chapter 12. And in Chapter 12, it's now addressing the types of bonds. I've got atoms. I'm going to connect those atoms, and that makes bonds. Okay? So in that, we get 2 types of bonds, according to Chapter 12. Ionic bonds and covalent bonds. You should, by looking at 2 atoms, be able to tell me, is it an ionic bond or a covalent bond? Okay? Sodium chloride, ionic or covalent? How do you know it's ionic? just for you, Dallin. How do you know it's ionic? Because you just erased it. That still doesn't count.
Because the chlorine is stealing the electrons from the sodium.
How would you know chlorine is stealing electrons from sodium?
Because the chlorine has a -1 charge on the sodium.
Unfortunately not. We can't pull it that way. I know where you're going with that, and that doesn't work. How do we know it's ionic? Might be useful if we had a definition for what an ionic bond was. Oh, we mean a metal and a nonmetal. Yes, yes. That would be a good bond. That would be a good thing. So that would be useful if, say, we'd come up with a way to determine, based on looking at the periodic table, what a metal and a nonmetal was. Did we do that? Yeah, how did we do that? Metals were left of the staircase. Our nonmetals were right. If we take a look at our periodic table, that's exactly what's happening with sodium and chlorine. Okay? So we've got an ionic bond. Okay? If we push this out and looked at our covalent compounds, let's see, do I have a picture? H2O and HCl. Whoa! Come back here. H2O and HCl. Okay? Ionic or covalent? Covalent. Why are they covalent? Both hydrogen, or all three, hydrogen, oxygen, and chlorine, are all found to the right of the staircase, making them nonmetals. So we've got a quick way to classify these. We could look at charges now for the ionic compounds, which fall out of that. Okay? We also now have a way to look at these as covalent compounds. Do we have further refinement necessary? If I threw water at you versus salt, you'd know the difference, right? Salt comes in as solid, water comes in as a liquid. Okay? So we could say the ionic versus the covalent bond changed phases. Cool. How about if I threw water at you versus HCl? Some people are like, I don't know what HCl is. Should we give it a name? Hydrochloric acid. I'm not throwing that at you. Also known as muriatic acid if you've done pool cleaning. Okay? That is not a pleasant compound. Its chemistry is drastically different than that of water. Maybe we need another bond type name. We do. We'll address it later. Right now, what we want to differentiate is first ionic versus covalent. Okay? In this video that you need to watch, hour-long beast, it goes through all of these rules. It tells you how to draw a Lewis structure. When it comes to Lewis structure, these are the rules you should follow. Okay? Other rules work. They get you an answer. They also completely remove understanding of the chemistry. This better represents how molecules bond and how they interact with the world. These rules don't screw you over if you need to move into organic chemistry. Every other rule set I have found, both in our textbook and online, screws you over when it comes to organic chemistry. Why do I care? I teach organic chemistry, and I'm tired of reteaching Lewis structure for the first 3 weeks. Okay? You're not taking organic chemistry? I'm very sorry for you. Okay? You are. You can talk to me in a little while. Okay? We'll pick up there Tuesday.